Hello everyone. Hope you are all doing fine. In this session, we're going to discuss about interfacing of memory and I/O devices. This is the heading of the unit, but the things which we are going to discuss are the address space, buffering, the different types of interrupts, and the different data transfer schemes. So let us start with the address space. What is address space? Address space means the virtual address your operating system can address. So this is the area which is addressable by the processor. The virtual address starts with 0 and can extend to the highest permittable limit by the operating system architecture. It is the amount of memory allocated for all possible computational entities like device, file, server, network, computer, whatever it is. So this is the allotted space for all these entities. A processor address space is always limited by the width of its address bus, because as many address spaces you can address, as many address lines you have in your address bus, that amount of address space is generated by the operating system for addressing. This is the concept of address space. Now, the next point which I would like to discuss is about demultiplexing. You've already seen in your diagrams in your 8086, or if you have discussed in 8085 also, that there are some pins where two operations, it acts as a pin for two operations, like AD0 to AD15. These pins are used for address also, for data also. Since address and data are not going to work simultaneously, these pins can be used for both the purposes. And definitely this is done to reduce the size of the microprocessor. So when these AD0 to AD15 pins, when we need to separate the address and the data from these pins, that process is known as demultiplexing. We'll see in 8086 some other multiplexed pins are there. The AD0 to AD15, A19, A16 and BHU bar. These pins are multiplexed pins. For demultiplexing, an additional 74LS373 latch is used to demultiplex this. So we'll see in a diagrammatic representation. Though here it is shown as Intel 8085 microprocessor, you can consider it to be an 8086 microprocessor also. See how when it from AD0 to AD7, since it is 8085, AD0 to 87 is shown, but when we consider it to be an 8086, which is AD0 to AD15. And we will get A0 to A15 on one side and D0 to D15 on the other side. So this is the concept of demultiplexing. And this is implemented by using the 74LS343 latch. Now let us see what is buffering. So when buffering is required due to the different speeds of the different devices. Sometimes it happens that some of the things you need to buffer for some time so that it is added to the other part to jointly perform certain function. So in those cases, buffering is necessary. The computers have different devices operating at different speeds. There are often multiple devices competing for the bus at the same time. So therefore, to allow transactions to occur in parallel, we should be able to keep the data in a buffer. So this is the concept of buffering. So we have seen there are two concepts. One is latches and the other are buffers. What is a latch? Latches are used to demultiplex. That means to separate the two things when they are multiplexed with the same lines. And buffers are used to drive external loads and to isolate component when disabled. So the address and data bus are multiplexed. We all know the ALE pin is used to control the latches, and buffered latches for A0 to A15 and A16 to A19 are buffered separately. You can see this in a diagram over here, where we can see the A15 to A19, A16 to A19 and the BHE bar line are buffered separately, and the other AD0 to AD14, they are latched and separated into data lines and into the address lines separately, and they are buffered separately. So this is the comprehensive diagram showing you the latches, the function of the latches and the buffer. Now we move on to the next topic in your syllabus, that is the interfacing part. Now you see, microprocessors and IO devices need to be interfaced. So there are two modes of interfacing. One is the memory mapped IO scheme and the other is the IO mapped IO scheme. In case of memory mapped IO scheme, the IO devices are considered to be a memory address. So what happens? The memory spaces, some of the memory spaces will be reserved for these IO devices because they are considered as IO devices. So what happens? The memory becomes less. So memory mapped IO scheme can be used for smaller systems. In case of IO mapped IO scheme, what happens is there is a line you must have seen in your pin diagram that is called the IO M-bar line. Using this IO M-bar line, the same memory spaces can be used for IO devices also and memory also. So this way what happens? No spaces are separately kept for IO devices. So we can accommodate more IO devices and the whole memory can be utilized. So IO mapped IO schemes are used for bigger systems. So we can see the differences in this slide in IO mapped IO and memory mapped IO. IO is treated as a memory in case of memory mapped IO, and IO is treated as IO in IO mapped IO. So more decoder hardware, less decoder hardware in case of IO mapped IO. In case of memory mapped IO, less memory is available, as I was telling you. But in case of IO mapped IO, the whole memory address is available. Memory instructions are used in case of memory mapped IO. Special instructions are required in case of IO mapped IO. Here memory control signals can be used. Here special control signals are used. Arithmetic and logic operations can be performed on data in case of memory mapped IO, but that cannot be performed in IO mapped IO scheme. Data transfer between register and IO is possible in memory mapped IO, and data transfer takes place between accumulator and the IO. So these are the basic differences between the IO mapped IO or memory mapped IO and the IO mapped IO scheme. Please be sure that the left hand side shows the memory mapped IO and the right hand side shows the IO mapped IO. Now let us go into the next topic, which is the interrupts. We are talking about the 8086 interrupts. Now what is an interrupt? Whenever your normal function is disrupted by something, we call it as an interrupt. So in a microprocessor also, when its normal program execution is disrupted by some request or by some operation, then it is termed as an interrupt. The interrupt may be caused by an external device. When it is caused by an external device, it is termed as the hardware interrupt. An interrupt caused by a special instruction is termed as software interrupt. Interrupts can be enabled, disabled, and masked. We will see there are some maskable interrupts, there are some unmaskable interrupts. The next exceptions are situations when function of the microprocessor is interrupted by some abnormalities in the internal condition. So they are called exceptions. So when we go for programming or we go for coding, we have to code certain things for exception handling also, which may happen due to some abnormal internal condition. So the interrupts in 8086, the hardware interrupts are NMI, which is the highest priority interrupt, and INTR, interrupt with lower priority. Among the hardware interrupts, NMI has the highest priority. So in case of software interrupts, these interrupts are implemented using INT N instruction, where this N can take a value from 0 to 255. That means you can go for 256 interrupts depending on the situation. Depending on the interrupt, the microprocessor will move on to the interrupt service subroutine and it will perform the function and come back to the original. So this is about the software interrupts. There is an interrupt called divide by zero interrupt. So what is this interrupt? When the result of division or div or IDIV instruction is very large to be stored in the designated location, this type of interrupt occurs. The single step interrupt, this is used while debugging an assembly language program. You have already experienced this maybe when you are doing your assembly language programming. When we try to debug it, we go step by step. We interrupt the program, the execution of the program, and we want to see the execution step by step. So that is called the single step interrupt. The next is the overflow interrupt. When the result of operation of two signed numbers is too large, when it is very big, which cannot be stored in the register or the memory which is designated, an overflow occurs. And the overflow flag, which is a status flag in the flag register, it is set to 1. When it is set to 1, interrupt service subroutine is executed in that. So this is one type of interrupt. Why are we calling all these interrupts? Because they are something which is disrupting the normal functioning of the microprocessor. So once this interrupt occurs, some subroutines are accessed and performed, and then the microprocessor resumes its original operation. So these are the interrupts of 8086. The next topic which we are going to discuss are the data transfer schemes. Definitely when you are connecting a device with the microprocessor, you got to transfer some data. And how do you transfer these data? So there are certain schemes. So data transfer always takes place between two devices. It is from the CPU to memory, or CPU to IO devices, or memory to IO devices. For effective data transfer, the timing parameters of these devices must be matched. So why we need different data transfer schemes? Because sometimes the device speeds do not match. Sometimes it happens that we have to keep on testing whether the microprocessor is free or not. So those type of problems have given rise to different types of data transfer schemes. We will see in the next slide. So basically there are two types of data transfers: parallel data transfer and the serial data transfer scheme. What happens in serial is serial data transfer scheme, also the parallels thing, the data is converted to serial data. So that is serial data transfer. So in parallel data transfer schemes, they are further divided into programmed data transfer schemes where CPU is involved, interrupt driven when the microprocessor is interrupted by the external device and then data transfer starts. And there is another data transfer scheme which is known as the direct memory access, in which case the CPU is not involved at all. So these are the different data transfer schemes. These are summarized here in this diagram. The parallel data transfer schemes are divided into 3 sections and the serial data transfer scheme into 2. Synchronous data transfers occurs when the speed of both the CPU and the device they match. Asynchronous data transfer occurs when there is a mismatch. Interrupt driven data transfer when the device interrupts the microprocessor for a transfer. And DMA data transfer is a transfer where this is used in case when there is a huge amount of data transfer required. So if we keep the CPU involved in this scheme, there will be underutilization of the CPU. So CPU is kept aside to perform other operations and the data transfer takes place without the involvement of the CPU. That is in case of DMA. So let us go to our next slide. So as I have already said, depending on the type of the device, data transfer may be synchronous or asynchronous. Synchronous is used when IO devices match in speed, and when the speed of the IO device and the microprocessor do not match, that is known as asynchronous data transfer. Some of the points are listed in this table. You can see synchronous, definitely When it works at the same speed, there's fast transmission. Synchronous is slower. In synchronous, you need a common clock signal. The same clock, the thing happens. Here, it's easy to implement. No need of clock sharing. And in case of synchronous, the CPU has to wait until the data can be sent. And in asynchronous, there is a scheme of handshaking. When the device is ready, it informs the microprocessor that it is ready, and then the data transfer starts. So in case of asynchronous, the CPU need not wait. It can send the device sends a signal when it is ready. All parallel transmissions are synchronous. Asynchronous transmission is used when data is sent, maybe through mouse or keyboard. So in case of interrupt-driven data transfer, the processor initiates the I/O device for data transfer. After it initiates the device, the microprocessor starts executing its own program. At the end of every instruction, the microprocessor checks if there is an interrupt from the device. If there is no interrupt from the device, the microprocessor continues its execution. So the time is not wasted. When the device is ready, from the device, it interrupts the microprocessor. And on receiving the interrupt signal from the microprocessor calls a interrupt service subroutine or routine to service the device. And finally, the data transfer takes place. So this is illustrated in this diagram. You can see. You see from the top of the stack, add, sub, and, or, NOP. So this way the instructions are to be executed. But after execution of that AND, we get an interrupt. Now what happens? The address is stored in the stack so that when the microprocessor comes back, it has to get that same address and continue the operation. So the address in the instruction register is stored in the stack, and the system moves on to an interrupt service subroutine. The third step, you see, interrupt service address is taken and it starts executing the subroutine. In the fourth step, after finishing the subroutine, it goes back, takes the address from the instruction register, and then continues the operation. So this way, interrupt-driven data transfer takes place. So long we've been talking the data transfer schemes which are based on by using the CPU. But in case of DMA transfer, microprocessor is not used. It disconnects itself from memory and I/O device by tri-stating its address and data and control buses. And the transfer takes place with the help of a DMA controller. The DMA controller controls the operation. There are two modes of DMA. One is the burst mode and the other is the cycle stealing mode. In case of burst mode, what happens? A block of data is transferred at a time. But in case of cycle stealing, the data is transferred when the CPU is found to be idle. In case of burst mode, the data transfer continues until the whole block of data is transferred. It is a very fast technique, and CPU utilization is less because as long as the transfer takes place, the CPU is idle. But in case of cycle stealing, when CPU is idle, the transfer takes place. So CPU utilization is higher. In case of burst mode, checking of CPU idleness is not required, but in case of cycle stealing, you get to check every time when the CPU is idle. When the CPU is idle, only then the transfer can take place. So these are the two different ways of DMA data transfer. So we talked about parallel data transfer. Now you see what is serial data transfer. Serial data transfer means each bit of the word is sent in succession. It means one at a time over single pair of wires. So when we want to go for serial transfer, a parallel to serial converter has to be used so that the incoming parallel data is converted to serial form and is sent out. And while sending, the least significant bit is sent first and the most significant bit at the last. Here D0 to D7 is used in case of 8085, but if you consider 8086, it should be D0 to D15. So this is what we had to discuss. I had to discuss in this session. Hope the session was fruitful. You can go through this and contact if you have any doubts. Thank you.